Hi everyone, welcome to Simulating Your Robot Brain with a Game Engine. My name is Paris.
And I'm Mars.
You can tweet at us if you'd like, we'd love to hear from you. We're authors, mostly writing about AI. Most recently we wrote about AI with Swift, but we've also written books on Unity. Currently we're writing a book on simulation-driven AI, which is kind of the topic of this talk.
So we're speaking to you today from Hobart. It's all the way down in Tasmania in Australia. You might not even know about that Australia has its own island state. It's the tiniest one, it's the coldest one, and everyone forgets about us. But it's gorgeous. It's totally lovely, and you should visit.
It's awesome.
So today we're here to talk to you about two things: machine learning and game engines. Two topics that are very dear to us in various ways.
So, AI has massively exploded over the past few years. All sorts of things have popped up, from AlphaGo for solving the specialized cognitive challenges of playing the board game Go, to DeepMind's AI for learning to walk in a visual robotic sense, to VizDoom, which was taught to play the classic video game Doom using only the input of the screen, no understanding of the game itself. There's lots of really complicated, rich scenarios for AI that can be solved in all sorts of ways, and many of them might benefit from some sort of visual or physical simulation component. AI is increasingly focused on these problems that span cognitive, physical, and visual, or some combination thereof. And because of this, particularly because of the visual element, game engines are really coming to the forefront of what's useful in the space of AI tooling.
So today we're going to talk about two frameworks. This is where Unity and TensorFlow come into the picture. Where Unity is a popular video game engine that accounts for about 60%-ish,
Huge amount,
depending on who you ask, of the entire video game industry. I would say everyone would have heard about Fortnite, which is not Unity, but almost everything else you've heard about in most mobile games. So the primary game engine by playtime, for sure. It's a powerful, flexible, well-designed game engine that can be used for everything from games to simulations to feature film VFX, and we're seeing a lot more of that nowadays, where we've got better projection and you can even put people in scenes. And those are all done with game engines because it turns out they're really powerful. And it's the software that my colleagues do most of their daily work with. And then on the other side, we've got TensorFlow, which is Google's very, very popular machine learning framework that came out of Python and has grown popularity, particularly with TensorFlow 2. It took on a lot of the properties of some of the third-party libraries that cropped up around it. And now most of the smart applications you'll see online will refer to TensorFlow or explicitly try to use something other than TensorFlow but still talk about TensorFlow because it's so popular. So the Unity game engine heralded their move into this space of AI with their release of this excellent paper in which they argued that their 3D physics-based simulation engine that had typically been used to develop video games was the perfect platform for generalized artificial intelligence. And anyone here who has done much ML would know that a long defining point of AI research was that everything has to be custom designed and targeted for each application of the technology. So you can see why this general part would be a big deal. They claim they had one framework, one engine, one piece of software, and it could do almost anything. So alongside this, Unity released an open source Unity plugin that allows environments made with the Unity game engine to be connected to TensorFlow through an inter-process connect called the ML Agents Toolkit.
It's awesome.
So Unity is particularly pushing very heavily into an area of AI called deep reinforcement learning. So now we're going to do a quick run through of what that means and why this is regarded as a generalized solution.
So deep learning is just the generalized term for things that have lots and lots of layers. Reinforcement learning, though, is where what we're talking about today comes in. In reinforcement learning, there's an agent, or multiple agents, and that agent exists in an environment. The environment exists for the agent to make some sort of observations in, perceptions, understanding of its environment, and then decisions are made. In the case of Unity, Unity calls the object that makes decisions a brain. The decisions are made and given to the agent to execute in the environment based on the observations the agent has sent back to the brain. And the brain makes a decision based on what the agent is perceiving about the environment, sends a decision back to the agent executes this decision, and then the agent and the brain are rewarded or penalized accordingly based on a policy until it has trained something that it does what it needs to do. So this kind of goes on and on and on until you have something useful. So when you train an agent using reinforcement learning, the decisions, they start relatively randomly. The brain just sends random signals out to the agent within the space of the actions it can make. And then the reward signals slowly guide that brain towards an optimal policy. So rewards penalize or reward the system for doing the right thing eventually, and eventually it converges on something useful. An optimal policy is just a fancy way of saying the reward signals make the brain get the agent to do the thing that you want it to do.
The learned behavior.
The learned behavior. So the three key parts of this, as far as we're concerned today, in this lightning quick overview of using Unity, the game engine for machine learning, are actions, where things the agent can do in its environment, observations, the things that the agent can measure about its environment, and rewards, which are the signals we give the agent and the brain to understand whether it's done the right thing or the wrong thing.
So by default, and as recommended by Unity, all of this is done using one algorithm, one system, called Proximal Policy Optimization, or PPO. Where the advantage of PPO is basically that it turns everything, no matter what the domain or what the goal, into an optimization problem, and then applies that simple philosophy to iteratively improve at whatever it's doing. So it's mostly fine to treat it as a black box if you don't know or can't be bothered working out how to tweak it, because it will do a good enough estimation. We handwave over it a bit here because PPO is an algorithm that's implemented through TensorFlow, and it communicates with Unity through Python to do the training. So this is great because if it means if you're comfortable with TensorFlow, you can control and tweak it from there, and you get as much granularity as you would using TensorFlow on its own, instead of fiddling about with Unity. But Unity wrote their own wrappers around TensorFlow to make it easier on you if you're the other side. So if you're not interested at all in TensorFlow, the ML Agents toolkit comes with a bunch of common configurations that you can use straight out of the box, and you only have to look at the Python end of the bridge when you press the Now Train button.
It's amazing. So before we give you a bit of an example of how you can use all this generalized artificial intelligence, PPO, Unity ML Agents toolkit to train something, we're going to give you a really quick overview of Unity. So we're not here to teach you game development, but we feel it's important that anyone who wants to get into this needs to understand how Unity works, even at a very basic level. So Unity, it's a game engine. It's great for building environments for video games, but it's also great for building environments that you're going to use for machine learning. Unity is comprised of, when you build something in Unity, the area is comprised of one or more scenes. A scene is basically just an infinite empty world in which you can add things. In this case, we've got a scene with a plane in it. Scenes are populated by game objects. The plane in the previous scene was a game object. Game objects are often represented by physical items like cubes or spheres or planes, but they can also be non-physical items. So things that exist within your scene might be visible, might not be visible, might have some physical component, might not.
A camera,
Camera.
something that emits particles.
Yep. A script that watches for something to happen in a scene is a game object that doesn't have a physical presence. Game objects in Unity are made up of various components. You can see the components stacked up on the side there. Components are both data and functionality. So a component can represent a position, a rotation, so a transform in the world, or it can just represent the fact that something has a certain parameter, or it can be a script, or it can be an asset that gives it a certain texture or a color. All game objects have at least a position, a rotation, and a scale, but they can have other components as well.
Seems kind of counterintuitive if you can have something that doesn't exist in a physical form and is just waiting for something to happen but still has a position.
Because it's a game engine underneath. So assets are anything that the game knows about. In Unity terminology, an asset is literally any file that exists in the system. Assets are scripts, textures, 3D models, neural network files, things like that. Most components are assets until they're added onto a game object. So you add an asset into a field on a game object. Basically, Unity is composed of pieces which are composed of other pieces, and using those pieces, you can build a scene. Remember, Unity is designed for video game development, so it's got a lot of terminology that's sometimes a little bit superfluous.
Highly modular. Once you figure out the pieces, you pick it up really quickly. But let's look now specifically at the Unity ML Agents toolkit. So there's two main parts. We've got the brain and the agents. That doesn't seem like it tells you much, so let's talk about them together. So they fit together like this, where there's only one brain, which is the thing that is learning some policy to do the thing that you want it to do, but it's typically hooked up to multiple agents. This means that each can be interacting with different scenarios, but each agent's repository of knowledge about its environment and where the decision-making is coming from is shared. So you can have two agents facing identical dilemmas at the same point. They should theoretically always do the same thing, but the potential for parallelism during training means that you can train a brain faster by just giving it more agents to learn from. It's a bit like if you had a time turner, you would have learned how to read if you could have 8 of you learning how to read, teaching the same brain at once. Very efficient. So going back to the actions, observations, and rewards from before, they fit in with our agents like this. Each agent will generate observations, which it then sends to the brain. It performs actions, which have been instructed to it by the brain, and then it will be assigned rewards, which it will then also tell the brain. The brain will then learn when it receives certain observations and follows up with certain actions. This yields certain positive or negative reward feedback. And that's what it can use to infer that what it just did was good or not without having to know what it was trying to do overall. It's like if you woke up in an obstacle course and every time you did a certain object, somebody gave you a candy, and every time you did another object, you fell off something.
I love it when that happens.
Stop doing the second thing and keep doing the first thing, even if you don't understand the scenario. So it's a very primal reward cycle. where if you just had an untrained brain here, it would just do random actions and it wouldn't get anywhere. But then our agents exist within our virtual environment, which is where it's generating observations of, and during training, the brain itself is deferring its judgment to a running TensorFlow process that's managing a neural net as it learns through that inter-process bridge we talked about before. So once the training is done, the neural net is locked in the state. Now it's got all its learning, we take it exactly how it is, and then we bake it into that brain object. So then in the future, when you're just up to the using the thing, and once you've done with training, you don't have to use the framework and get rid of the process altogether.
So we're going to do a quick demo using Unity. We hope it all works properly. We love demos. We're going to show you a little robot that we've built because we figure it's a good way to see how it works visually. We could abstract this to something very non-visual, but because Unity lends itself to very visual problem solving, we thought we'd try something visual. So I'm going to show you Unity now. In Unity, you're going to see a little robot. The little robot is going to be designed to push a crate into a certain target. We'll step through that for a moment. So here's our robot. He's pretty cute. It's called Little Beepo, but sometimes we call him other things. We have gendered the robot. We're not sure why. The goal of this environment is to teach Little Beepo, the robot, to push the cube, this cube, into the goal area. So the goal area is this thing over here. Each time this simulation resets, the cube changes its position, as does the goal area. So the goal area can be on one of the sides, and the cube can be anywhere within the environment. I think the robot also has a random position. So the goal here is for this robot to push this cube into the goal. The robot has a physical simulation attached to it, which means it is in a physics engine. So because this is a video game, we can say these things exist within a physics engine. That means the robot can push the cube around. So the components that are attached to both the cube and the robot allow them to push each other. So if the cube is rammed into by the robot, it can move it. Going back to our actions, observations, and rewards, the robot's action abilities are movement. It can move one of 4 directions for each single step of the simulation. So by altering its direction between steps, it can even move diagonally. This is just a side effect of being able to move in 4 directions very fast. As I said, because there's a physics simulation happening, it can push into the crate and move it around. So you can see here the 4 different directions that the robot can move in. Those are the actions, okay? So in the context of making random decisions, the only random decisions that the brain can feed into this robot are backwards, forwards, left, or right. That's it. So we're training it to use the ability to make those actions to push a cube around. The observations for the robot are slightly more complicated. So the robot has 14 different raycasts. A raycast is like a perfect laser measuring beam that tells you exactly how far away it is from something and what that something is. So in this case, the 14 raycasts are made of 7, which come from the bottom of the robot in various angles, and another 7 that come from same direction slightly above the body.
So it works something like LiDAR and has about 180-degree vision.
Or like those laser measuring things you can buy to measure your house, where it like tells you how far away something is, but in this case, instead of just also measuring it, it tells you what it is as well. So like if I pointed it at Mars, it would say Mars is, 30 centimeters away from my hand. And that it was Mars. So here is an emphasis of some of these raycasts. Raycasts are a pretty standard technique in 3D graphics and video games. They're used by things to tell them how far away they are from other things. In this case, the observations of the robot, the things it perceives about its environment are how far away it is from things that these rays can see. As far as rewards go, when the agent pushes the crate into the goal, it gets a large reward. So it gets a whole bunch of points. This is entirely arbitrary. As with many things in machine learning, the rewards and the numbers of the things you give it are often more of an art than a science. So this is based on trial and error and us picking a number that works based on training the robot to do what we want it to do. It also gets a small negative for moving at all. So every single move, every single action the robot takes in this environment is penalized. And that's because we want it to economize. We want it to solve the goal, solve the problem using the fewest possible steps. So we want it to be able to push the crate into the goal without wandering around the room.
So here it's not so much the values as the proportion between these two values that matters. It doesn't matter that it's 5 or -1, it matters that it wants to get the thing in the goal about 5 times as much as it wants to not go in the wrong direction.
Yes.
So The first step after building an environment like this is the training. We run the simulation at high speed, letting the agent take random actions and writing out to a neural network file with the weights being influenced by the rewards given for these random actions.
We actually do it multiple times simultaneously, as we said before, parallelism.
Yes, and even though we can see in this environment, we can look at the little robot moving around, we can also run this so fast you can't even see it. So you don't have to run it slow enough that you can see what he's doing, but you can if you want to, and then you can see him get better over time. But you can run this super fast and multiple times at once, many instances. So then this training process involves that Unity ML Agents Toolkit command line tool that you connect TensorFlow and Unity together. And you can monitor the trading process using the tool output, so you can just look at your average rewards or losses that change over time, like you can see down the bottom. But also, because it's just TensorFlow, you can use the full suite of industry standard tools like TensorBoard to monitor your agent's success, because you get all the shiny stuff that goes with TensorFlow normally. And this just basically means you get to make lots of useful graphs about your little bot getting better.
If you don't know what any of this is, the gist is you really want to make the graph go up, because that's the reward that the bot is getting. Cumulative reward over time is really the only graph that matters. You want it to go up.
Getting better is his job. So look at him go.
There's him moving around now, solving his little problem. And you can see he's pretty good at this, right? He does a pretty good job. Sometimes he pushes in the wrong direction, he very quickly fixes it. Look at him go.
He's so good.
He's very, very good at what he does.
It's definitely a side effect of having these like visual problems. If you can see it, you have like this sense of pride when it gets it right.
Yes, here you can see his LiDAR raycasts going off. So these flickering green lines are his raycasts showing you what he is perceiving. I think he's very good at his job. He's certainly better than I am at pushing a cube around. So we've also built a really simple self-driving car just to quickly show off how behaviors emerge. This car taught itself to drive. Admittedly, it's a little wobbly, but it was only like 3 to 5 minute training cycle. It gets rewarded for not hitting barriers, going forward and getting further along the track. And it gets penalized if it hits a barrier. So it's actually pretty good for only a couple of minutes of training around this little racetrack. The car actually has a totally different observation system to the little robot, and we thought we'd throw this in at the end here just to show you that. So the car actually is a forward-facing camera all of its own, and that is the only observation. So instead of measuring distance to things on the track, you can see this little camera here in the corner, and that's actually mounted to the front of the car and is feeding into the machine learning system to teach the car that the walls are bad. So when it hits a wall, the only information it has is the camera is very close to a wall, and that's all it has to learn from.
It also doesn't know what a wall is,
Yeah.
or a road is,
Or
what depth is.
So the camera doesn't measure any distances from anything, it just solely uses that camera input to understand its world. And through convolutional neural nets and so on, the machine learning system figures out what you need it to do based on the reward structure. There are lots of fabulous demos in the Unity ML Agents Toolkit if you're curious. We highly recommend you check them out. It's a really fun environment. This is a walking one where the thing has learned to walk by flinging itself forward by moving its joints. Highly recommend you look at this.
This is why we gave little Beepo some detriment to using unnecessary energy. This is what happens if you just let them run rampant. They find a more optimized way to run if you don't account for the energy being used.
It's really fun.
So you can use this for other forms of learning, like behavioral cloning, where it learns from human-provided demonstrations, or there's all sorts of combinations of the different algorithms that come with the toolkit. And there's so many possibilities, because by generating hundreds of thousands of simulations of an environment within Unity, you can learn policies for even very complex environments or problems where the number of observations an agent can perceive or the number of actions they can take are enormous.
Massive.
And different settings can even allow agents to take on factors that have been historically incredibly difficult in machine learning, such as tasks that require memory, or require multiple agents to work together, or have varying sequential objectives. It's just crazy. But that's all we have time for today. So I want to leave you with a bit of a so what? What's the point of all this? And it's hard to say what a generalized AI solution is good for, just like it's hard to summarize what just AI is good for in one slide. But it shows great potential for a whole range of different applications, simply because you can visually and spatially map problems, whether or not they themselves are visual or spatial in nature. And you can solve them in a way that's easy to visualize, easy to demonstrate to others, easy to iterate on, and it's just plain fun.
So thank you so much. We've put our Twitter handles here. Please tweet at us if you're interested or you want to have some questions with us. We'll try and tweet out some links during the conference. We're really sad not to be there in person. We hope it goes fabulously anyway. We hope to visit one day. Thank you very much for watching our presentation. Check out our books if you're interested. Thanks again. Bye.